So the first section in chapter 21 was the idea of current and resistance, how those things are pretty much opposites of one another. How would you define current if you had to simply give me an idea of what current in electrical systems or electrical circuits is? What is the current?
Electricity flowing through a conductor.
Perfect. Electricity flowing through a conductor. Okay, that conductor could be the metal wire. It could be the bulb and the filament in the bulb that's a conductor. It could be the battery. The battery itself is a conductor also. They have to be conductors for it to flow. If they were insulators, it would impede the flow. What's a resistor or what's resistance? How would you define that? Give me an analogy if you want. Give me an idea of what you think it would be.
Something that stops the flow of electricity.
Yeah, something that cuts off the flow of electricity. Very good. So you can think of it as like a backup in a pipe, or if you're thinking, we talked about human bodies with like high cholesterol, it's the plaque on the inside of the arteries of your body that stops the flow. It slows it down. So that was really the idea from chapter 21, section 1. We had a couple formulas. First, we defined current as delta Q over delta T. And then we defined Ohm's law with V equals IR. So we're looking at these two formulas here. Okay, these two formulas right here. The second one is the one that we used throughout the rest of the chapter. The first one we really used for one simple example. You don't really need to be worrying about this for a mathematical example, but this concept that current is really the amount of change in charge. That's how much charge passes a given point in a given time period. Charge over time. It's how much charge passes a given location. It's like how much water is flowing out the end of the hose. When you water your garden with a garden hose, the very end of it, think about how much water is actually flowing through that in a given time period. You would call that, in terms of fluids, you would call that volumetric flow rate. Think about gasoline. It's how much gas you're pumping every second, or gallons of gas, or in this case might be cubic meters per second. That'd be a volumetric. This is charge over time. But again, current, I want you to understand, is a rate. It's a rate because it's divided by time. So it's a rate that something is occurring. In this case, it's the rate that electricity is flowing. So that's where that definition will be useful. I don't want you to practice. You don't even need to practice that with math, okay? We did one example just to talk about with a refrigerator, startup, running time versus actually running. But don't focus on that mathematically, excuse me. Focus on V equals IR, and then the next couple things we're going to go through. In this section, we also talked about several different things. We talked about things that are ohmic versus non-ohmic. Things that were ohmic had constant resistances. So for example, a light bulb in that simple circuit lab, you guys measured the resistance when it was in series by using the multimeter. And the resistances were on the order of around 700 ohms. They were pretty constant. They didn't change at all. Now, if you left that circuit running for about an hour, what do you think would happen? Or an hour, 5 minutes, not even an hour. Just 5 minutes straight, you left the circuit on, the bulb was on the whole time for 5 minutes. And then you go back and measure the resistance. Come on, figure this out. After 5 minutes, what do you think will happen to the resistance? What do you think?
Increase?
Why?
Because the temperature increases.
Yeah, remember we talked about the factors that affect the resistance? You have length, cross-sectional area, you have temperature, and then the material itself. And that's in this section also, but in that case we're talking about temperature. So there would be a material that for the most part is ohmic, but a light bulb like that, like the old incandescent light bulbs, they used to heat up. And when I was a kid, my dad used to teach me to change light bulbs by, you take as a young boy, you take your shirt off, or take like a cloth, something, a material, use your sleeve, and you have to actually just use that to unscrew the bulb. Or else what's going to happen, you're going to burn your hand, right? You'll end up burning your hand by touching it. Now the bulbs that we use, the different ones, I forget what they're actually called. Anyone know the actual terminology? Fluorescence?
Or LEDs.
Okay.
That are a lot softer.
Yeah, I know LEDs for sure. Yeah, that makes sense. And then fluorescents are these guys that go like this? Yeah, that like spiral. Anyhow, the temperature change could cause the resistance to change in the actual bulb itself. If the material were different, it would have a different resistance. I sent you a really short video, maybe like 15 minutes yesterday, of just where electricity, how it flows, the whole idea of how AC versus DC works. And in part of the video, they talk about the fact that really we could use silver and gold as our conductor, but we use copper. Why do we use copper, you think? Why do we use copper? I mean, use common sense.
It does the same thing, but it's cheaper.
Yeah, it accomplishes the same thing, but it's cheaper. So the resistances for copper and aluminum and gold and silver, and there was another example, I forget what the fifth one was in the video. They all have about the same resistance, actually. Okay, they all allow flow to occur, but why would you use something that's really rare and expensive to have electricity flow when you don't need it? It doesn't do it any better really than copper does, at least not to any significant value. In this section, we also talked about potentiometers. A potentiometer was something that was a variable resistor. The example that was given was a joystick or a volume dimmer or a light dimmer switch where the resistance changes, and as a result, the actual brightness of the bulb we're thinking about changes. In your lab, we didn't have time to do it, but on the circuit board, I think I mentioned it real quick, there was one potentiometer. And the potentiometer, all you had to do, some groups actually did, I'm going to get to this. All you had to do was network this in. So before you went to the bulb, if you networked the actual potentiometer in here, you could adjust the brightness of the bulb using this little, what looks like a dimmer or a joystick in a sense. It allows for a variable resistance. We talk about superconductors in this section. What was a superconductor?
Something that can conduct without heating up at all.
Close. You're on the right track.
Without there being like resistance.
Good. Without there being any resistance. In essence, it does not heat up because it has to be very cold. So you're on the right track there. So it has to be super cooled, something that's below a certain critical temperature that allows for zero resistance and flow. That is analogous to frictionless surfaces. So think about when we've talked about like a hockey puck or an ice skater. We said, it's almost frictionless, right? Metal on ice is really close to frictionless. That's how bobsleds work and stuff in the Olympic Games, or what's the other one? The luge. Have you seen the luge? Have you ever seen the luge? It's wild. They're going at like 50 miles an hour down this pipe in this metal container. Like, that's kind of scary when you think about it. And they're just like laying down and controlling it all. But why does it all work? Well, because it's like a frictionless surface, the metal on the ice. That's what superconductors are like for circuitry. Let's see, anything else in this section? Now let's press on. Now, in the second section, we started talking about series versus parallel circuits. So let's get to the major points for this section. We had a lot of formulas, but they're all on your formula sheet. Remember, all the formulas I'm going to show you for this, for voltage, current, and resistance in series and in parallel, are all on your formula sheet. You need to know what they mean, though, the understanding of the plus versus the equals. That's what you're noticing. It's either a plus sign or it's an equal sign. It's the only difference in these formulas. So we start with series. We see that we have a battery, networked to one resistor, networked to another resistor, and back to the source. Now, this is series because nothing branches off. You don't see a separation of flow anywhere. The minute you see two branches to the pipe, you got to start thinking about that's probably parallel. Okay, it's parallel. Now, if hypothetically, take a look at what I'm going to do. I'm going to erase this in a moment, but take a look real quick. If I did this and networked a wire in right there, it looks like a branch, so you want to say parallel, but that branch would cause a short in the circuit. It would cause the electricity to flow in this direction. It would say, you know what? There's no resistance this way. I'm just going to go this way. And that's called a short in the circuit. So these elements would no longer bear the load, so all the electricity would go through this wire because it's easier resistance. So it would sit here and do this for a while until it heats up, and then it would start to burn. That's a short circuit. When two wires touch earlier on, it's a short. So if I did that, that's not a branching. That is not parallel. Okay, that's not parallel, just so you're clear on that. Oops, let me go back to that circuit. So we've got a little battery here, connected to one resistor, to another, and back to the battery. Now, in series, we know three things. First, we know that the current in the system in series is equal throughout. Why can I say that? Why is the current the same for all resistors? What is 1 and 2? What do those mean, by the way? 1 and 2, the subscripts. Because they're on your formula sheet. It says 1, 2, ... I think it says N afterward. What's the 1, 2? What is that indicating as a subscript there? The current through what? Yeah, the current through whatever resistors you have. So in this case, we have two resistors. So we have the current through resistor 1, which is how much flow is going through here. The current through resistor 2. And then IS is the current supplied in series. S for series, P will be parallel. But whatever's over here in the formula is what's being supplied by this battery. So as a result, what we're seeing here is that the current supplied by the battery is the same throughout both resistors. Because there's no branching off. That's how you need to think about this. If it's in parallel, which we're going to draw on the bottom here now, if it's in parallel instead, we know that the current itself will split. It'll split to both of these segments. And here's what's going to happen. Follow the marker. It'll go like this. Here's the current. It's flowing along. And then suddenly the current is going to go along both of these paths and then it's going to come back together and come all the way back over. So you'll see the branching off here. So the current itself splits up. So for this one, what can I write? What can I write for the second one? For parallel. The current in parallel equals what? Not 1/2, but you're on the right track. He's saying 1/2 because he's saying half the current to each. I get what you mean, but how do I write it? How did I write it in the formula?
1 over I.
That's the R one. You're thinking of R. That's for the resistors. It's 1 over R1 plus 1 over R2. That's resistors. What is this one?
I1 plus I2.
Yeah, I1 plus I2 plus ... In this case, yes, it's just I1 plus I2. But this is a sum, because think about it. If I were to physically measure the current flowing, let's say the current here was 10 amps when it comes out of the battery. Well, if this is 10 amps right here, what's going to happen? It's not necessarily going to be half, by the way, okay? It depends on the resistance of each of these. If this has a higher resistance, it's going to get less current. If this has a higher resistance, it'll get less current. So what will happen is maybe 7 amps will go this way, and the other 3 amps will go this way. And when they come back together, how many are they going to be again? 10. Going back to the battery is 10 amps. Coming out of the battery is 10 amps. That's why there's a plus sign here for this. Is that clear? This plus sign indicates that you sum the two branches together to get the overall current. Whereas here, the current is the same. Now, voltage, to simplify things, you listen to this in the video. I explained a lot of the theory when I was not here that day when you listened. But the theory for voltage, to simplify it, is it's the opposite. Okay, so for voltage here, we've got the voltage in series is equal to the sums. So this is a plus sign now, whereas earlier it was an equal sign for series. And then for parallel, the voltage drop is equivalent for all of them. And what this means simply is this, and you did this in your lab. You literally did this. Does anybody remember what the voltage for the battery was around? Anybody remember what the battery voltage was for those big, you have it right next to you if you want to even look. But there was a rating on the battery. How many volts was it? Who remembers? From your lab?
15.
1.5, close, not 15, 1.5. And it was 1.5, and what you noticed is when we had two resistors, this is what you did in the lab right here. You had two resistors, and usually you were getting like around 1.4 or 1.5 when you actually measured it. And here you would get like 0.8, and here you get like 0.6. It wasn't exact. You noticed there was a little bit of voltage loss due to the wires. So you had pretty much the idea that the sum of these two voltages that the bulbs are getting equaled the original voltage. Because voltage, you should think about energy. Remember, what's the other definition of voltage? It's called potential difference. Potential difference. Those charge carriers have a lot of potential energy when they leave the battery. Then they lose a bunch of it here. Well, they still have some. They lose the rest of the energy here. And then when they get back to the battery, how much energy do they have? None. And then work gets done on them by chemical energy in the battery. It charges those charge carriers, and they move along again. So this is a cycle. It's a cycle that continues. In parallel, though, the voltage is the same. So if this is 1.5 volts, both of these get 1.5 volts. Because of the way that they're connected, they're both directly connected. They both get the full 1.5. That's why when it was in parallel in the lab you did, the lights were a lot brighter. Because these were both getting a full 1.5 volts. Whereas here, the voltage was being split amongst those two resistors. The last thing we did for this, was resistance. Resistors in series, to get an equivalent resistance, was the sum of the resistors. So if I wanted to replace this circuit right here, let me put a little line so you know that we're separating. Okay, that's series up top. If I wanted to replace this circuit with an equivalent circuit, I could draw something just like this right here, with one resistor instead. And if this resistance was 2 ohms, and this was 5 ohms, I could simply write here 7 ohms. And that's the exact same circuit. This is an equivalent circuit. That's why you saw REQ, equivalent. I'm putting an S for series, so you know it's the equivalent series resistor. In parallel, though, you can't just add those numbers together. In parallel, it was 1 over the resistance in parallel equals. And this is what a moment ago Tiana was talking about. Okay? It's 1 over. So this is a little bit more difficult with math. That's all it is. So if you have, God bless you, if you have resistors of 5 ohms, we'll do 5 and 2 again, so we have the exact same numbers. You can see how the answer is very different. If you have 5 ohms and 2 ohms, you got to put those in here for R1 and R2. That makes that 1/5 plus 1/2. A half is 0.5, A fifth is 0.2. 0.5 and 0.2 is 0.7. So mathematically speaking, this becomes 1 over RP equals 0.7. Well, that's not what RP is. How do you get RP? Switch these two. Take 1 over 0.7, or just do the inverse of 0.7 to give yourself RP. Okay, that'll be, instead of 7 over 10, it'll be 10 over 7. So the overall resistance in this series, in this parallel circuit, could be replaced with one resistor here. And this will yield an overall resistance of 10 over 7 ohms. Okay, this will be around 1.5. So that would be this resistance over here, 10/7. So notice what happens. Here's where your theory and your multiple choice kind of questions come into play, right? Notice what happens. In series, if I take two resistors, let me zoom out so you can see the original. In series, if I take two resistors, take a look up here, please, and I sum them together to make one circuit or one resistor in that circuit, the value goes up. You literally sum these numbers. This goes up. Yet here, you had 5 and 2 to start, and your answer turned out to be around 1.5. So in parallel, when you link together a bunch of networks in parallel, the overall resistance of the network goes down. The overall resistance goes down. Okay? So that's what I want you to pick up on when you look at the simplification. Let's do one quick example of simplification with both. Okay, let's rotate so that's actually straight. There we go. Give me numbers. Doesn't matter what they are. Give me numbers. Go ahead, 10. I got it. What else? Keep going. One more. Thank you. I do that to be annoying, but also to prove to you guys that you can literally make your own problems up, right? So we take a look at this network here, and we think to ourselves, wow, we have a lot going on. It looks like we've got a branching somewhere. So what do I think when I see a branch? Parallel. And then I see that I have several consecutive resistors, which makes me think that these two are in series. And these two here are in series. Take a look. We got series here and series here. So let's simplify the series wherever we can. Makes it easier. Replace all the series with one resistor in those spots. So what's 10 and 5, obviously? So we replace that with 15 ohms. Get rid of these two resistors here and put one in its place. The 12 that's there we'll leave alone. The other one, though, is 15 and 6. It's 21. Bring them back all the way around. And we got 9 volts. Okay, that's all we can do for now. Yet, we notice that there's another branching occurring. So let's take the 12 and 21 and do what with them? What do I do with the 12 and the 21? The 12 and the 21, what are they in? The what? Yeah, add the reciprocals. They're in parallel. Add the reciprocals, exactly. So remember, the formula for this is when it gets a little tougher. Let's write it out. It's 1 over R1 plus 1 over R2. And notice the only ones that are in parallel are these two right now. The branching occurs here, so it's what happens after the branching that's in parallel. So these are in parallel with each other. We'll replace them with one resistor we're going to get for this number, and then this resistor that's going to go here to replace the both of them will be in series with this one over here. So how do I add these together? I can't do it in my head. I really don't want to do this with fractions. Use your calculator. Literally, you guys I don't have a calculator. Do 112 plus 1 over 21. Add them together and then do the inverse of that. Add those fractions together. Give me a decimal, please. Give me that intermediate step so I know what it is. And then do the inverse of that number. What's 112 plus 121st? Go. 0.13? Yeah. Now take the inverse of 0.13. Go ahead, Eric.
7.6.
Thank you. So that's our resistance that takes the place of these two resistors right here. Yes?
How do you do the inverse of 0.13?
You could do 1 over 0.13. Just switch these two spots. Right? Think about this as like a little equation right here. V equals x over t. You could flip-flop. So just switch those two. 1 over 0.13. It'll give you around 7. Yep. Or there's a key on your calculator that says x to the negative 1. That's inverse. You could use that key also, whichever is faster.
Yeah, how did you get 7.6?
Inverse of this. Because look, it's 1 over RP equals this decimal. 1 over RP equals 1 over R1 plus 1 over R2. Add these together to get this decimal, but this is in a denominator. You've got to switch these two. 1 over 0.13 will give you 7.6. So I rewrite the series, the circuit now as the following. 9 volts attached to 15 attached to 7.6. Remember, what I circled up here is now gone. I've replaced these two resistors right here with one simple resistor down here. And now these are in series, so what do I do to their values? Simply add them. Again, guys, got to know this stuff. You went over this in class once. You should have done these for your problem set already. This should be really you should be flying through this. 22.6 will be our overall resistance of this network. Now, I've got the overall resistance of the network. I've got the overall voltage of the battery. What can I determine if I wanted to? Using Ohm's law. The current. Ohm's law is V equals IR. You've got the voltage. You've got the overall resistance now. You could find the current using, again, V equals IR. Be prepared to do something like that. 21.3, the whole idea about power, we had 3 formulas. The first one, IV. The second one, I squared R. The third one, V squared over R. Which of these are you going to use? Which one? Come on, what's the overall answer to this question? It's a trick question, right? Which of the 3 are you going to use? Could you answer that right now?
We don't have any numbers.
Thank you. It depends on what you're given. And I said there's a general answer, right? So whichever one you're given, if you're given the resistance and current, you'd use the second one. If you're given the current and the voltage, use the first. If you're given the voltage and the resistance, use the third. It doesn't matter which one you're going to use here. These are very simple problems. It got a little bit tricky when we went to the idea of cost, right? For cost, we said, well, cost is really the amount of energy consumed times the rate that energy costs you. If it costs you 25 cents per kilowatt hour in New York City, that's your rate. If you use 30 kilowatt hours of energy, that's how much energy you use. So this problem is only tricky because it's like, how do I get energy, right? How do I know how much energy I used? Well, go back to earlier in the year. This is what you studied in this video. Earlier in the year, we defined power as the amount of energy transferred over time. So if I want to get energy in that formula, how would I solve for capital E in that formula? P times T. So it turned out that the power consumed by an appliance times the time you consume it for goes in place right here. This formula is on your formula sheet. Cost equals, I think it is. Cost equals energy times rate. I forget when I laminated your formula sheets, if it was last year or if not. It should be on the electronic. I know it's on the electronic version, but I'm just worried that's not on the ones that are laminated, because those are laminated, I think, 2 years ago. So power times time goes right here. So you take the power consumed by using one of these 3 formulas, times, and that power you're going to get an answer in watts. But because rate is always given in kilowatt hours, there's dollars per kilowatt hour, you have to have energy and power in certain units. So the energy has to be in kilowatt hours. So when you look at time has to be in hours, and power has to be in kilowatts. So run through the last example in 21.3 for sure. I could try numbers real quick if we don't run out of time, but make sure when you get a power in watts, you convert it to kilowatts by moving 3 decimals. The time it takes, or the time you're running your appliance for, let's say it's 120 minutes. Would you use 120 minutes? 2 hours, because you want it in hours. The power consuming, or the power you're using times the time you use it for, times the rate at which you're getting it. This is usually given in dollars per kilowatt hour. Okay, that comes right off of your energy bill. It's at the bottom usually. It says like 20 cents per kilowatt hour, whatever the rate you're paying. So mathematically, if you want to quickly look at one of these, let's say we've got, So we've got the current flowing through a device to be 12 amps. We've got the voltage supplied as only, let's say 120 volts. We want to figure out over a time period of 150 minutes and a rate of 23 cents per kilowatt hour, what does this cost us to run? Okay, given the current running, the voltage supplied, the time it runs for, and the rate. You need all this information. If you didn't have the current and voltage, maybe you have the resistance. That's fine also. But you need at least 4 variables here. You need time and rate always. And then you need either 2 of 3. Either current and voltage, current and resistance, or resistance and voltage. So you start by finding the power. Since I have I and V, I'm going to use P equals IV for power, because that's the formula with I and V in it. Multiply those two. We do 12 times 120. That's going to be 144. If we do 12 by 12, so 144, and tack on a 0. That's how much power we're using. But that's not the answer. I need this answer in kilowatts. So it's 1.44 kilowatts. Remember, it's got to be in kilowatts. That's the power consumed, or the power that's being used. Now I remember that my formula is cost equals energy times rate. And energy is power times time times rate. So really, all I'm doing is taking that power of 1.44 kilowatts, times the time, times the rate. The rate is fine. I've got that on the end. But what's the problem right now? What am I missing? What am I missing? The time. The time is 150 minutes. What is that? 2.5 hours. Okay, remember, you have to convert that into hours always. So if I multiply this by 1 hour over 60 minutes, I'm doing the conversion up top. It's dimensional analysis, remember? Multiply by the conversion factor. 150 over 60 gives you 2.5. No, definitely. You can do it in your head. You can do it wherever you want. As long as you get it right, it's fine. If you get it wrong, though, and you have no work, that's a whole other story, right? So what do we end up getting at this last part? 1.44 kilowatts for 2.5 hours at 23 cents per kilowatt hour. Just multiply across. You're going to end up with only dollars as your units because kilowatt hour cancels. What do we get? Who's got a calculator that can do some quick math? What do you got? 0.82? Thank you. So a little under $1. A little under $1 we're looking at here. And it seems about right. You're taking 2.5 times this and then multiplying by around a quarter. Around 1/4, 1/4. Hey, what questions do you have? I kind of went abbreviated there because I knew there was a lot to cover.
How many kilowatts? I was like running my AC before I went to sleep. I was like,
It says it on the AC unit. It really depends on each. I know that a cell phone only draws like 6 watts of energy. Of power. 6 watts. That's what a cell phone draws. Oh, for sure. If you leave an AC running without like being on like energy save mode, you probably spend like at least 50 cents a night, at least. So $15 a month on top of their bill, which is probably already like $120 or something. The refrigerator is like that. It's always running.